This is the sound of a quantum computer.
Sounds absolutely nuts.
Unlike anything you've seen before.
Quantum supremacy.
Sounds a bit sporty.
Controllable randomness.
Both 0 and 1 at the same time.
Dental floss.
Loom oven with calcium inside.
Cryogenic refrigerator.
Electrons sloshing around.
Dental floss.
There's a parallel universe in which you're indeed a rock star.
Going to the moon.
In particle physics labs all over the world, people are trying to perfect quantum computers.
They're a new type of computer that exploits the unusual laws of quantum physics to work faster and frankly weirder than anything on your desktop. And they could be the start of something truly revolutionary.
Like many world-weary rationalists, we've been contradictorily praying for some miraculous technological fix to civilization's most pressing crises: environmental destruction, famine, disease.
Constant buffering on Netflix.
And now we could be on the verge of finding that fix.
What, just for the buffering or for the survival of humanity stuff as well?
Shh, I'm Jim Mauldleman.
And I'm Stuart Horton.
And this is Stupid Qubit, quantum computing for the clueless, where we'll be trying to find answers to all our dumb questions about a technology that's got us more excited than anything since Space Invaders.
Questions like, what exactly is a quantum computer? And will I be able to make one using the bits I got from the Mapping clearance sale?
Do they really work across parallel universes? And if so, how do we know we're in the universe where they give us the right answers?
How do you program one, and what games will it run?
Are they on the verge of cracking all our encrypted internet communications? And what difference will it make if I delete my web history now?
Who's funding the technology? And should we be worried if they have Analytica in their name?
Will these machines attain consciousness and wipe out the human race?
Or figure out the meaning of life and save civilization?
And when will we get our intelligent, matter-manipulating quantum smartphones?
Hello, and welcome to episode 2 of Stupid Qubit, Quantum Computing for the Clueless, the only podcast understood by more listeners than presenters. Sorry it took so long, but in our defence we're all subject to quantum effects on some level, and we may have experienced some fuzziness and decoherence around the festive period.
Plus, as Brits, we've been a little distracted as our own entangled state careers towards seemingly inevitable collapse.
So, to recap, last time we immersed ourselves in quantum weirdness, found out what a quantum computer is, and got our hands on one of the world's first commercial machines, IBM Q, which lives in a cryogenic fridge that looks like the TARDIS control console, where it's partly held together with dental floss.
Then we learnt about qubits, the building blocks of these machines, which are a bit like the transistors or bits in a conventional computer, except they're governed by a spooky principle of quantum physics called superposition, which essentially lets them represent the numbers 0 and 1 at the same time, possibly in parallel universes.
And by using another weird quantum principle known as entanglement, scientists believe they can connect loads of qubits together to create machines capable of processing unfeasibly large numbers at mind-boggling speed, giving humanity the power to understand and model complex systems like molecules, the weather, or the workings of a brain.
Unfortunately, before they can succeed in attaining what's known as quantum advantage or
quantum supremacy,
the point where these machines can outperform conventional computers,
they face another thorny problem: how to construct qubits stable enough to work in the way they need without fizzling out or decohering before they've had time to finish their sums.
And although we'll soon see machines with over 100 qubits, we discovered you can't judge the power of a quantum computer simply by the number of qubits it has.
People are building, connecting and controlling qubits in lots of different ways. Some work better than others, but none yet work well enough to do the really exciting, world-changing stuff.
Last time we focused on the approach that's currently the most advanced, superconducting qubits, the type used in the pioneering machines starting to appear from the likes of IBM, Google and Rigetti Computing. And although the qubits in these machines are still highly fragile and prone to errors, there's nonetheless hope that they may soon be able to do some pretty exciting stuff.
This episode we'll be looking at how Microsoft believes it can leapfrog the competition with its proposed topological qubit, built using an elusive particle that no one had seen until a few years ago, and inspired by a 500-year-old technique devised by the Incas.
Our topological qubits are knots and braids. Knots and braids in space-time.
We'll also be meeting some of the pioneering scientists behind the UK's national programme to build a quantum computer by trapping and levitating ions in a vacuum.
Any old ion?
Any old ion?
Any old ion?
No, just ions of calcium, strontium and ytterbium.
Ah. Helping us in our investigations will be Star Trek fan and Professor of Quantum Technologies Winfried Hensinger from the University of Sussex, He tells us all about his breakthrough blueprint for a warp-speed quantum computer bigger than a football pitch.
What we do is just beyond belief.
And Oxford University Professor Simon Benjamin, who told us all about parallel universes last time, is back, along with junior research fellow Vera Schäfer, to explain their part in the creation of a modular quantum computer networked by light.
This is already better than anyone else has done with dot ions.
And we'll find out if we're moving into a new era where quantum computers that don't work properly might still start doing some incredible stuff, like solving the energy crisis, for example.
That could just really change everything.
Plus, stay tuned for more quantum questions, details of our as yet unclaimed Adiabatic Award, and an exclusive qubit giveaway. But first, let's round up some of the quantum news that's caught our attention since the last episode.
PhD student Urmila Mahadev at UC Berkeley has solved one of the fundamental problems in quantum computing.
The so-called quantum verification problem essentially asks, how do you prove a quantum computer has solved your calculation correctly when you can't see what it's doing while it's doing it, and classical machines aren't powerful enough to check the result?
Urmila spent 8 years at graduate school working on the puzzle, which she solved using nifty cryptographic techniques.
Nifty cryptographic techniques? And what were those exactly?
Well, Stu, Urmila tweaked and combined some highly sophisticated principles of encryption in a particularly artful and clever way.
Can you be more specific?
It says here she used trapdoors and secret states.
What, like a David Copperfield extravaganza in North Korea?
Look, clearly it's far too complex to go into the specifics here, but there's a very thorough article about it which we'll link to on our website in case any listeners want a more mathematically literate explanation.
Researchers Matt Otten and Stephen Gray at the US's Argonne National Laboratory have found a new way to reduce the effects of noise in quantum computers.
The new technique involves repeating the quantum experiment many times with slightly different noise characteristics, then analysing the results.
Otten said, "It's like taking a series of flawed photographs. Each photo has a flaw but in a different place in the picture. When we compile all the clear pieces from the flawed photo together, we get one clear picture."
It's hoped the new method will increase the chance that near-term quantum computers might actually be able to do something useful.
French atomic energy researchers at CA d'Armel de France have built a novel computer model to help them explode molecules in just the right way to forge perfect nanodiamonds.
The tiny jewels, 1,000 times smaller than a grain of sand, have applications in quantum computing, optoelectronics and medicine.
Now the team will be able to make all the nanodiamonds they need. Not to mention a tidy revenue stream supplying engagement rings to Poundland.
There was another big splash across the channel as IBM announced the opening of its first quantum computing facility in France.
The IBM Q Hub at the University of Montpellier is open to companies, public organisations and academic institutions that want to try out the tech.
France seems a particularly suitable location for quantum computing research, as the Gallic Shrug is believed to exhibit quantum effects that might make it suitable for the fabrication of qubits.
In the moment of peak shrug, it's thought that a Frenchman's shoulder blades actually exist in a quantum superposition of up and down.
And they can presumably be entangled with a string of onions.
So is jocular racial stereotyping okay now then?
Yeah, Brexit dividend.
And what about misguided jingoism?
Soon to be compulsory.
Huh? Okay.
Now, most of the traditional tech companies making quantum computers today are building machines that are, however you look at it, less than perfect. In the next few years, these machines will probably contain up to a few hundred qubits, but those qubits will still be very fragile and error-prone, so it's unlikely they'll be able to scale up easily, and the jury's still out as to whether these imperfect machines will be able to do anything useful at all.
But one of the computer industry's biggest names, Microsoft, is going out on a limb and trying to build qubits that will be able to scale effectively from the off.
As we understand it, the basic idea behind these topological qubits is to chain a load of electrons together like beads on a string and tie up the ends with some mysterious and elusive subatomic particles called Majorana fermions.
Microsoft claims that this stringy structure makes its qubits stable enough to get straight on with the job of building a large-scale logical quantum computer that will make current machines seem about as impressive as an egg timer.
The company originally said we could speak to one of their top quantum buds to ask how they were getting on with this potentially epoch-making endeavour. But in the end, they were all too busy fiddling with their qubits to find time to chat before our deadline, so instead we've cut together some snippets of recordings we made at a Microsoft event back in November 2017, where they brought their top quantum researchers to London to explain all about their topological qubit. Here's Professor Leo Kouwenhoven from TU Delft in the Netherlands, who's leading Microsoft's quantum charge.
You can imagine it as a row of electrons occupying a row of seats that is completely filled, except for one chair. Then if everybody goes over by one chair, what happens to the empty seat is that it jumps over to the very other end. And in superposition, the empty chair is actually at the same time left and right. One of the electrons actually splits up in two pieces, it fractures, and the two pieces are now at the very end of the system. And these two end states are known as the Majorana particles, predicted in 1937 by an Italian physicist, Ettore Majorana, but only detected in 2012 in our lab in the Netherlands. So this becomes a very stable, robust building block for making a full-scale quantum computer. Normal qubits, if you want to scale it up, it's like building a house of cards. It's a nightmare for engineers. While if you have a Lego building block, it's going to be fun to build up to larger structures.
Topology is the branch of maths concerned with morphing shapes, and the reason they're called topological qubits is because you'll be able to bend, twist and braid them together without destroying the information they hold. Dr. Krista Savore, a principal researcher at Microsoft, likens the principle to the way the Incas stored information in knotted braided strings called quipu back in the 15th century.
If my information is stored in chalk marks or drawings in the sand, it will wash away. But if I had stored my information in knots, this is robust to a storm. Our topological qubits, in fact, are knots and braids. Knots and braids in space-time rather than a physical string. Now, if we want to compute with this type of qubit, take a few of them, and it's just like a braid. And I can create these intricate patterns just like the Incans did with their quipu. And in fact, these patterns allow me to complete complex operations and solve very challenging problems. If I wiggle the strings of my braid, it doesn't change the braid. And that's the key. This is far more robust than other types of qubits and other types of quantum computation because it's robust against these local noise effects.
So Leo thinks topological qubits are like Lego bricks, but Krista seems to be describing something more like Scooby-Doos or loom bands.
Maybe they're both at the same time. So how many of these uber qubits have Microsoft managed to make so far?
Well, we're not sure they've made any. They've been fairly tight-lipped about how far advanced they are. Now that might be because they haven't got very far, or it might be that they've succeeded but don't want to publish details in case it helps their competitors.
But even if they have succeeded, this is Microsoft technology, so no doubt it will take another couple of years to install all the updates.
It's funny you should say that, because even though their quantum computer doesn't exist yet, they have released a software development kit for it, but more about that next time when we cover quantum programming. Either way, no news is good news for us Brits, because it means our plucky little island nation still has a hope of snatching quantum glory from the jaws of the corporate tech superpowers.
And we're going to do it our way.
Because we don't need slick superconducting circuits.
Or showy-offy space-time braids.
No, we just need to shoot microwaves at some charged atoms levitating in boxes in a vacuum. Because we're British. And it's a bit eccentric.
Although several US, Japanese, Austrian and Israeli labs are also doing it.
It's called ion trap quantum computing, and we'll be telling you all about the UK's efforts to conquer the field right after
the Stupid Qubit Adiabatic Award.
If you listened to the last episode, you might remember we were baffled about a class of quantum computers known as adiabatic. These were the first type of commercial quantum computers to appear, and although they have thousands of qubits, they don't perform logical computing operations, and no one has successfully managed to explain to us how they work.
So in a bid to tease out a legible explanation, at the end of last year we announced the Stupid Qubit Adiabatic Award on our social media feeds. Anyone who can explain how these machines work in a way that we can understand has the chance to win a spectacular kinetic atom trophy, as well as the chance to come on the podcast and clear up our adiabatic confusion. So far, only one person has had a go.
Physicist Sam Mughel from Barcelona, one of the founders of a company called Multiverse Computing, tweeted us the following explanation. 1. Sure, your problem is mathematically identical to finding the most stable state of an exotic quantum material.
We're doing stereotypical racial accents now as well, are we?
Yeah, I told you earlier. Brexit dividend.
We don't even know he's Spanish. He tweets in English. His phraseology would suggest a fluent command of the language. As far as we know, he's got impeccable pronunciation.
Fair point, but it's still funnier. So from the top, 1. Sure, your problem is mathematically identical to finding the most stable state of an exotic quantum material.
Jesus Christ.
2. Simulate that material with your quantum annealer. 3. Drive your annealer to its most stable state. And 4. Measure. And voila.
Now, the problem we have with Sam's explanation is, although it tells you exactly how to work an adiabatic quantum computer, it doesn't tell you how an adiabatic quantum computer works. We want to know what's going on inside the machine once you let it loose on your problem. What are all these qubits that aren't logically connected actually doing?
So, no award for you yet, Sam, but if you want another go, feel free. And sorry about the accent thing. Likewise, anyone else who thinks they can clear this up for us. Now, as part of the £270 million UK National Quantum Technology Programme, the government has been funding an initiative called the Networked Quantum Information Technologies Hub, or NQIT for short.
And Simon Benjamin, the Oxford University Professor of Quantum Technologies, who told us all about parallel universes in episode 1, is also one of the NQIT's associate directors.
Yeah, well, first of all, I have to tell you off for calling it NQIT, because we've been advised to pronounce the Q with a K sound, so that it comes out as NKIT, because kit is very empowering and exciting and sounds a bit sporty, whereas quit sounds terrible.
NKIT.
Sorry.
So that is the UK's big collective effort on building a quantum computer. And it's led by Oxford University, but it's actually an alliance of 9 universities and over 30 companies.
So, according to the NQIT website, you're hoping to build a hybrid light matter quantum computer called the Q2020 engine, which is based on a type of qubit known as an ion trap. So, what's the plan, and are we going to get there first?
Well, it depends what you mean by getting there first. So Google has 72 qubits on a chip. Now that's more qubits than we have working here in Oxford by far at the moment. But if they want to then go to a larger number of qubits, they will have to produce a new chip and solve a new set of problems. Our aim is to make a little 5-qubit quantum computer that's too small to do anything very exciting, but then connect it to another little quantum computer so that they actually join up and become a slightly bigger one. So it's a network approach based on wiring together little gadgets, linking them up with light with optical fibers. Then the point is, once you've connected together 2 5-qubit gadgets, then you can have as many as you want. Well, it's expensive, but because you've now learned to link them together, then the sky's the limit. So that's our plan. And getting to large-scale devices that, say, have a couple of 100 qubits that are working very well with very low noise levels is a very desirable goal. And I think there's an excellent chance that we can actually be the first to do that.
So what exactly are ion trap qubits, and why is it, in your view, they offer the best hope for realising Britain's quantum ambitions?
I wish everybody the best of luck in trying to make their particular kind of quantum computer. I mean, there is, of course, a sort of competitive element to it, but I would be delighted to hear that any given research team, whether it's commercial or academic anywhere in the world, had suddenly done a big step forward and was now working with 200 qubits or something. That would be brilliant, because mainly I just want to see these devices exist, because I think that'd be fantastic. Now, ion traps are not the only thing the UK does. We also have a superconducting effort here in Oxford under a guy called Peter Leake, and we have an effort with diamond materials and so on. So ion traps aren't the only horse we have in the race.
Or indeed the only ion we have in the fire.
So what is an ion trap? The answer is really simple, actually. As long as you can understand what an atom is, and of course atoms are just the basic units that all material is made of, then what an ion trap does is it starts off by taking atoms and flicking off one of the electrons so that the atom has a net charge, and then we call it an ion.
Have you ever flicked off an electron, Stu?
No, but I once went quantum tunnelling in a research park off the A1.
Sorry, carry on, Prof.
So an ion is just an atom that's been robbed of one of its electrons. And the reason you do that is once the atom is charged, once it's an ion, it's easier to grab it and move it around using electric fields.
And why do you need to do that?
The ion needs to be held in place in a vacuum so that other atoms can't come and knock it around. So just imagine a little box. There's nothing in the box, it's a vacuum, except for a small number of ions which are being held in place in the middle of the vacuum. Now that is a wonderfully isolated quantum system because nothing is touching the ions. And that means that if you treat each ion as a qubit, and they make excellent qubits, so you can put them in two different states, say a low energy state and a high energy state of the ion, that's your 0 and 1, and you can put it into a superposition of the two.
So what makes an ion-trapped qubit better than a superconducting qubit?
Because it's so isolated, it's in the middle of a vacuum, not touching anything, it lasts for ages, or ages in quantum terms. Here in Oxford, we've made them last for 50 seconds. So, that's a proper long time. You can have a conversation whilst your qubit lasts. And in fact, there's other work around the world that we could copy if we wanted to, which shows them lasting for 10 minutes. Whereas for the superconducting systems, you're looking at the merest fraction of a second, perhaps something like 100 microseconds. So they last for ages because they're so well isolated. And they also can be controlled to a very high fidelity, perhaps 5 or 6 times higher fidelity than superconducting qubits. So they're really the gold standard qubit.
So do your qubits need to be cooled in a steampunk super fridge like the superconducting ones?
Ion traps do not need to be at these exotically low temperatures, colder than interstellar space kind of thing, that superconducting devices do. It's not fundamental for us to go for low temperatures at all. It is fundamental for us to have a vacuum, so that's our burden. So the burden for superconducting systems is to have an exotically ultra-low temperature. The burden for ion traps is to have a high-quality vacuum. I would say that the high-quality vacuum is the lesser of the challenges.
The vacuum chambers that house the modules, or traps, look a bit like vintage deep-sea divers' helmets, spheres of welded metal the size of a human head. Although with the right manufacturing processes, they might be able to shrink them down to about the size of a fingernail. Each trap contains a small number of ions of calcium and strontium, which act as the qubits, and these can be manipulated by lasers and microwaves.
The idea is to connect the modules together using a photonic link system, being built by a group at the University of Sussex.
Photonic link system? That definitely sounds like something out of Star Trek. The photonic link system's malfunctioning, Captain. I can't hold the ion in superposition for much longer.
Well, actually, photons are particles of light. The idea is to use them to transfer the quantum information from qubits in one module to qubits in the other, by entangling them with the ions in one trap and then sending them down optical fibres to another one.
So, how close are we to getting this thing all linked up and working properly? Here's Simon Benjamin again.
I'm a theorist, not an experimentalist. I work closely with the experimentalists here, but I'm always very impatient. I'm sort of like a designer who's impatient to see the design realized. So I'm always over there saying, does it work yet? Does it work yet? Does it work yet? But experiments are tricky things, components break because it's all research level stuff. And so it's never possible to give a strict arrival time for these things. However, being able to link up two separate units to the sort of quality that we need is certainly a goal for this year. Having done that, how long it takes to then have, let's say, 100 or 200 modules like that all linked together becomes an engineering task. And that could happen very quickly if we were able to partner with funders and commercial entities that wanted to see that happen, or it would happen more slowly if it was down to us to do it.
We recorded this interview with Professor Benjamin last summer, so did NQIT hit its goal of linking two modules together last year? We'll find out in a minute from one of the experimental physicists building the machine itself, but first...
Quantum questions, quantum questions, quantum questions.
Last time we asked you to send us any questions about quantum computing that you wanted answered, however stupid. We weren't disappointed. Jesse Kester from the Netherlands emailed to tell us he wasn't crazy.
Always a bit of a red flag, to be honest.
And to ask whether, presuming our universe is, as Elon Musk believes, a computer simulation, like the Matrix, quantum computing could actually represent humanity performing a speculative execution attack on that simulation, which lets us exploit all the cheats and shortcuts we weren't supposed to see, kind of thing.
Jesse postulates that if humankind succeeds in creating quantum computers, it could alert the designers of the simulation we're living in to the exploit, which might cause them to patch it, after which we would no longer be able to observe any quantum effects in our universe at all. All our quantum computers would simply stop working, thus proving the conjecture that we're living in a simulation.
So, yes sir, there are 2 points that need addressing here. First, creating advanced simulations of entire universes would undoubtedly require the power of highly advanced, probably quantum computers. So we reckon any perfectly simulated universe would by definition also have to contain a perfect simulation of quantum physics. Thus, we'd contend that the quantum effects we observe in our possibly simulated universe are more likely to be a conscious part of its design rather than a coding flaw.
Second, we note that you're from the Netherlands, Schäfer. Maybe take it a bit easier in those Amsterdam coffee shops, mate.
Quantum questions.
Martin tweeted us to ask, if neutrinos can pass uninterrupted through thousands of miles of solid matter, will they ever be of any practical use to those of us without a disused mine full of chlorinated water?
We presume you're referencing the nuclear power industry there, Martin.
However, according to astrophysicist and author Ray Jayawardena, neutrinos have lots of as yet untapped uses, such as remote detection of illegal nuclear facilities, a means of X-raying the Earth to discover stores of precious minerals, and even as a way of speeding up long-distance communication.
Scientists have already successfully encoded binary messages into these nippy little uncontainable particles, and Jayawardena believes that neutrinos could one day be used to communicate with extraterrestrial life across interstellar distances.
Because, hey, you never know how many aliens have got a massive neutrino detector set up on the off chance that some alien civilization might want to send them an interstellar email.
Don't forget, if you've got any dumb
quantum questions,
you can tweet us at Stupid Qubit, leave a comment on our Facebook page, or email us at hq@stupidqubit.com. Now, back to the UK's Q 2020 engine to find out whether they've successfully connected two modules or not. Here's Vera Schäfer, a junior research fellow at Oxford who's been working on the machine for several years.
We already have successfully linked these two different modules. People in my group made some great progress last year, so they built these two separate vacuum chambers. We call our two Alice and Bob, and entangle ions within the two different traps via a photonic link. And they have now made both of them work, and they've got entanglement with fidelities of over 90%. And an entanglement rate of over 30 Hertz. And this is already better than what anyone else has done with trapped ions, but they think they can even further improve this in the next few months or weeks even.
So how long before you start connecting additional modules and scaling this thing up to a size where it can do more complex calculations?
So we're in the planning stage for that, but maybe in a year's time, but that's a very rough guess, I don't know. And the next step that we want to do before adding more modules is do some interesting physics, for example, entanglement distillation.
Distillation? It can make booze too?
Ion brew, presumably.
No, so the higher our fidelities, the better these processes work and the faster we can do them. In the end, we want to have a very high fidelity entangled state. And with the photonic link, that is hard to do on first try. But if we have a high fidelity entangled state on one side, we can transfer that entangled state over the link to the other trap over and over again and throw away the back bits, the errors. And this way get a very high fidelity entangled state between the two different traps.
Last year, Vera's group made a significant breakthrough by finding a way to speed up the process of connecting or entangling qubits at speeds between 20 and 60 times faster than was previously possible.
And now she's working on something called cross-species entanglement.
What, like making centaurs and pegasuses and stuff? Cool.
No, and I'm guessing it's got nothing to do with Richard Gere either. An ion species is just the material it came from. In this case, calcium and strontium. The team need to be able to get the two different types of ion to talk to one another properly, which is what they're working on now.
We still have some fairly large errors, but we found a lot of problems and fixed them in the last few weeks. So it's some exciting weeks of work.
Great, so it sounds like Britain could soon have a quantum computer with hundreds of qubits then. So will these be proper, fully functioning error-corrected qubits like Microsoft is trying to make, where every one you add doubles the power of the machine?
Unfortunately not. Our qubits aren't going to be the kind you need to build that full-scale, fault-tolerant quantum computer, at least not qubit for qubit, but they still might be able to do some useful stuff. Here's Simon Benjamin again.
Let's suppose that we built 200 modules linked up together. That's still not enough for what you're referring to as fault-tolerant, full-scale quantum computing. For that, you need something like 10 million qubits. That's the sort of number you need to shoot for.
So, like the superconducting quantum computers we looked at last episode, the Q2020 engine is going to be an imperfect machine that can't run complex quantum programs because the qubits still fizzle out when you're trying to get them to calculate stuff, right?
You're referring to what's starting to be called the NISQ era of quantum computing, an acronym that stands for Noisy Intermediate Scale Quantum Computing. Now, all around the world, people are turning their attention to is how to get useful performance out of near-term quantum computers. That is very tough because it's basically saying, my computer won't behave itself, but how can I make it do useful stuff anyway? And we're working on that here in Oxford. For example, solving a chemistry problem that chemists could not solve by any other means. And that's something that my research group is now working very hard on, for example, is if you've got, let's say, 200 qubits, they're working well, but they are imperfect. Can you discover new drugs, new kinds of material? Might such a machine even be useful in machine learning? These are the things that we're furiously investigating. So we're hoping that a combination of our architecture, which gives us high connectivity, and the quality of the ions that's already well demonstrated, will make it a superb near-term quantum computer, as well as an approach which can eventually give us the full-scale, fault-tolerant version. But the answer still might turn out to be no.
And being optimistic about the future, which isn't easy for us Brits at the moment, what specific problems might these imminent NISQ machines be able to tackle?
Whether it's in the NISQ era or whether we have to wait for the fault-tolerant large-scale quantum computers in more like 15 years' time or something, I think we might see a golden age of rapid discoveries in material science and in chemistry. So suppose that we were able to find ultra-high performing solar cell materials by simulating them in software in a quantum computer. So then it became very cheap to have extremely efficient solar absorption just all over the place, on the sides of buildings and so on. That would be transformative for society. That could just really change everything.
But some in the field believe we won't see any transformative breakthroughs unless and until we get a large-scale, fault-tolerant quantum computer. And that's probably at least a decade away, possibly several.
In the meantime, why not play with your own qubit? Because we weren't joking when we promised you a free qubit. So if you'd like one, just retweet the link to this episode on our @Stupid Qubit Twitter feed, and or share the post pointing to it on our Stupid Qubit Facebook page. Ideally with a nice comment encouraging others to listen.
Then email us at hq@stupidqubit.com and we'll send you your free qubit. Some manual construction involved, although our qubits demonstrate superposition and entanglement, we do not guarantee they will be able to perform any useful logical calculations.
So in that respect, they're just like everybody else's. Now the Q2020 engine isn't the only ion trap quantum computer under construction in the UK. Over at the University of Sussex, where, as we mentioned before, they're making the photonic link system, a separate group under Professor of Quantum Technologies Winfried Hensinger is hard at work on another machine.
In 2017, Hensinger's group, which is also part of NQIT, published its own blueprint for a scalable ion trap quantum computer. And although it'll be modular like the Q2020 engine, Hensinger isn't interested in building a NISQ machine. Like Microsoft, he says he's shooting straight for the kind of large-scale device that could be a real quantum leap forward for humanity.
For me, it has never been such an attraction trying to find applications for small qubit numbers, because I really want to tackle the really interesting things. Quantum computers offer the opportunity and the possibility to simulate nature in an entirely new different way, and this in turn then may find a cure for dementia, make new materials. Really, the opportunities are endless.
So what first inspired you on this quest to build a potentially world-changing machine?
Star Trek. Even in primary school, I watched Star Trek and was a big fan, and I'm still watching Star Trek. And yeah, for me, it was always like to explore something entirely strange and mad, and it couldn't be anything more mind-blowing and strange as quantum physics. What we do is just beyond belief. And so for me, my ambition has always been to go faster to these really large qubit numbers. And so this is what we're trying to do in my group at Sussex.
Unlike Microsoft's proposed topological qubits, however, he's going to need quite a few more of his ion traps to do it. While Microsoft reckon they can build a large-scale quantum machine with around 2,000 of their qubits, quantum computers based on other technologies like ion traps and superconducting circuits would need millions or billions of connected qubits to do the same thing.
Because, as we found out last time, most types of qubit are very fragile and sensitive to noise. And by noise, scientists mean any environmental disturbance, not just someone shouting at them. And this makes them prone to going wrong. So to build large-scale systems on these technologies, scientists will have to bundle lots and lots of qubits together and get them to act as a single logical qubit.
Which begs the question, if they're so efficient, why isn't everyone just working on topological qubits?
If Microsoft are successful, this would be obviously an extremely powerful method to build a quantum computer. The problem with topological qubits is nothing has been demonstrated yet. And so in a way, what Microsoft is doing is really a high-risk, high-gain, blue-sky research. And if they are successful, that will be a most amazing and most fantastic thing. But it is equally possible that they won't be successful. So if that's the case, obviously, then we're going to have to stick with the quantum computing platforms and implementations, which have already delivered quite fantastic results.
Which means Britain really could be in with a chance of being first to build one of these truly revolutionary large-scale quantum computers. So, how does Hensinger's ion trap machine differ from the Q2020 engine, and why does he think it's better placed to scale up to really big qubit numbers?
Well, his team have made a couple of really significant breakthroughs with their blueprint. First, they pioneered the use of microwaves to control the qubits, which is easier to scale up than the method more commonly used in ion traps, which is to control each qubit with its own pair of lasers.
And if you then need millions or billions of quantum bits, you would need millions or billions of pairs of laser beams. What we invented 2 years ago is a new technique based on the use of microwaves, where you can replace these laser beams with voltages applied to a microchip. So obviously then you need millions of billions of voltages, but that's a lot easier to achieve than making use of millions or billions of pairs of laser beams. And in fact, it's very similar to transistors in a conventional computer.
And your other fundamental breakthrough was finding a much faster way to connect all the ion trap modules together, is that right?
So the 2020 engine, that's a really beautiful design, but this design relies on photonic links. Now this is a very powerful and very, very interesting technique. The only problem is, at this point, it's still very, very slow. So we asked the question, is there a different way to connect two quantum computing modules? And we came up with a very, very simple solution. And instead of using photonic interconnects, it is possible to use electric fields to connect quantum computing modules. What we do here is we shape the electrodes on the edge of each quantum computing module in such a way that the electric field lines connect. And what we can do then is we can literally transport an ion from one quantum computing module to the other quantum computing module. And we can do this with a connection speed up to 4 orders of magnitude faster than using these photonic interconnects.
4 orders of magnitude, of course, being not 4, but thousands of times faster.
Exactly.
And you hope to have a prototype machine ready soon, is that right?
So what we work on right now at the University of Sussex is to optimize this technology. And we expect to have a first prototype that makes use of this technology operational in less than a year.
Fantastic. So how many qubits will that have, and what will it be able to do?
So here we're really not trying to increase the number of qubits. If you keep on adding 10 qubits or 20 qubits, then it's going to be a very, very long time till you reach 1 billion. What we're trying to do instead is to perfect the technology so that then we can manufacture quantum computing modules, and then we can very, very quickly to go to large qubit numbers. Now that's still an immense challenge, but I think one thing we can certainly say is that there is no obvious reason why you can't build a large-scale quantum computer using this technology. And I think it's fair to say that we don't have to conquer any more fundamental physics challenges in order to make this happen.
So what challenges do you have left?
One of the most difficult thing is to bring all of these engineering bits together in a single machine. And so let me be very clear that while we have certainly simplified the construction of practical quantum computers, by no means is it now easy to build a large-scale quantum computer. But what it means is we can now focus on some of the challenging engineering to achieve that point.
And it doesn't get much more challenging than trying to put together a computer with billions of electrified modules in a high-quality vacuum covering an area bigger than a football pitch and probably sucking up enough juice to power a small town.
So, the big question. How long do you think it'll be before Britain is ready to unveil its world-beating ion trap quantum computer?
So a lot of people trying to make this up as some funny competition where one group is just going to do this on their own and just build a quantum computer. And that is utterly stupid.
Yeah, stupid. Yeah, of course that's stupid. But is Britain going to get there first?
You know already how utterly stupid that is when you look at the development of conventional computers. So there was a lot of steps between ENIAC and the iPhone you might have in your pocket, right? So in quantum computing, we are extremely thankful for all the quantum computing efforts around the world. So it's an international thing where many different groups are contributing in order to make this technology a reality. My group, in fact, very much relies on this talent. So I'm extremely lucky of having some most amazing scientists from around the world in my group.
But do you think you'll be the first? Microsoft reckon there's a 50-50 chance that they could build a large-scale, fault-tolerant machine within about 10 years.
So first of all, I mean, the 10-year timescale is probably a pretty reasonable timescale. It's probably for us, that is kind of the order of magnitude as well, which we're envisioning to go to really large qubit numbers. But having said that, nobody can make any predictions on a timescale of 10 years. And if anybody claims to you they can make reliable predictions on a timescale of 10 years, then you should probably have your own thoughts about that.
Well, here in the UK, no one can make any predictions in the timescale of 10 days right now, let alone 10 years. But I'd like to hope we're not still talking about Brexit in a decade's time.
Well, if we do crash out with that deal, by then half the country will probably have had to try and eat the other half.
We are definitely getting eaten, Stu. The other half have got all the hunting rifles. And violent thugs.
Yep, we are Soylent Green, mate. Although, I do reckon we could take that bloke with a mullet that runs Wetherspoons.
Gammon, tasty. But what'll happen to the UK's quantum computing programme after we Brexit? I couldn't help noticing 2/3 of the UK quantum scientists we've spoken to have been German.
And we didn't mention the war once.
Who needs war when you've got Brexit on your doorstep? Why should we have to fight any foreigners? We're a proud nation and we voted for Europe to leave us alone so we could fight amongst ourselves.
Seriously though, the science and technology community is very worried about all the Brexit uncertainty. If they're going to succeed in realising these potentially world-changing feats of physics and engineering, our quantum technologists need sufficient funding and the freedom to collaborate internationally.
And as yet, they've had no assurances of either. Here's Vera Schäfer.
The science community is one of the most international communities, so it's a big worry. In my group, there are lots of different nationalities, and I think we worry a lot about it. And even English scientists worry about it, that maybe they think they want to leave the UK if a hard Brexit happens, because they're worried they won't get the funding anymore in the UK or won't be able to collaborate with the people they want to collaborate with. So it's definitely a big worry. But then you also live in a very different world here, because no one I know thinks Brexit is a good idea.
And what does Professor Winfried Hensinger think?
Quantum computing requires the very best and brightest minds, without doubt. This is so hard to do, and so we really need amazing people. And so it's very important that Britain is open for business. And so we need to make sure that whatever happens, we are able to attract the very best minds to Britain after Brexit. Working collaboratively close together around the world is extremely important. And what all of the scientists in this field are trying to do is to encourage politicians to assure that we can do that, because it's not just good for science, but it's really key to ultimately achieve economic prosperity for Britain.
And of course, it's the founding philosophy of the Federation in Star Trek.
Indeed, absolutely.
That said, at the time of recording, there are no signs of any softening of Brexit that would lift the threat hanging over many of these scientific projects. So, Professor Hensinger, if we do career headlong into a hard Brexit, how can we ensure you'll stay to complete your machine?
You might have to hide me in your loft.
You'd be more than welcome in ours.
Fantastic. I hope you have a big loft.
Well, it's not quite the size of a football pitch, but we can move a few suitcases. We're not paying your power bill, though.
So, Brexit aside, how do we sum up the excitement and potential around the UK's ion trap qubit building endeavours?
I feel a song coming on.
This is an original tune. Any similarity to any copyrighted works is unintentional and purely coincidental.
They're caught in a trap that could work out the cause of life and much more, maybe. They could be the key that cracks reality, helping us perceive the world in new ways. When we connect together superpositioned ions, Britain can build her dreams on superpositioned ions.
And that's it for this episode. We'll try and be a bit quicker getting the next one out, but no promises.
Thanks to all the scientists who put up with our dumb questions.
Next time we'll be learning how you program a quantum computer. What can you make them do now? And what stuff have people already got lined up for when they are working properly?
And we'll find out what the quantum computing community is doing to ensure that anyone who wants to has the opportunity to devise killer quantum apps that could save the world.
Qubit.